Ladies and gentlemen, Software Incorporated is proud to present the third generation of its flagship product, AxSTREAM 3, a software suite for conceptual design, analysis, and optimization of turbo machinery. This demo will provide a general overview of AxSTREAM 3 features and methodologies. The scope of AxSTREAM suite. AxSTREAM can be used to design and analyze all types of bladed turbo machines that use compressible gases. The various machines include axial multistage compressors and single-staged fans, axial multistage steam and gas turbines, radial inward flow turbines, mixed flow turbines with radial and axial parts, single-stage centrifugal compressors, multi-stage centrifugal compressors, integrally geared centrifugal compressors, axial radial compressors. The concept of design and analysis in AxSTREAM. AxSTREAM was created to assist turbo machinery engineers with two of the most important activities in their work, which are design and analysis. The software enables engineers to create new machine designs from the very beginning, starting with only a few parameters about the machine they are looking to make. It also allows engineers to analyze and estimate the performance of existing machines with efficiency in mind. The existence of these two capabilities defines the major benefits behind the AxSTREAM suite and also two major modes of its operation. Ultimately, the design tasks are performed in design operation mode, and the analysis tasks are performed in analysis mode. The difference between the two modes lay in the nomenclature of AxSTREAM's inputs and outputs for each mode. In design mode, AxSTREAM uses design specification data as input, which includes boundary conditions, geometry constraints and some non-dimensional parameter that govern design. The output of the design mode is 3D blade surfaces and meridional geometry. In analysis mode, AxSTREAM requires the input of basic flow path geometry. Basic geometry includes meridional dimensions and span-wise distribution of cascades principal parameters. The outputs of the analysis mode are performance estimations and different charts. AxSTREAM Suite Architecture. AxSTREAM Suite software architecture is highly integrated. All of the AxSTREAM modules use a common database. Therefore, there is no need for any special data conversion operations to transfer data from one functional module to another. AxSTREAM main solvers are enveloped in different interfaces. Inverse solver is an engine of preliminary design solution generator and post-design task. Direct solver is an engine of mainline streamline tasks, design of experiment module AxPlan and map generator AxMap. The main functional modules have a local databases. This two-level database organization prevents occasional damage of the project data. Also, the loadable models functionality allow the users to add to AxSTREAM their own loss and fluid models. AxSTREAM Suite is vertically and horizontally integrated product. As a vertically integrated product, it provides all phases of conceptual design including preliminary design and sizing, post-design adjustment, mainline, 1D, and streamline, 2D, analysis coupled with design of experiment and map generation, profiling blade 3D design, 3D finite element-based structural analysis 3D Navier-Stokes CFD analysis. As a horizontally integrated suite, AxSTREAM provides services mentioned above, for all types of bladed turbo machinery, that is, axial turbines, axial compressors, single-stage centrifugal compressors, radial inward flow turbines, multi-stage centrifugal compressors, axial radial compressors, and integrally geared compressors. Design analysis process in AxSTREAM. One may note that in AxSTREAM, the large amount of attention is paid to design phase. Why it is so? If we'll take a look to typical gains vs expenses diagram, we'll see that most effective part of design is preliminary design. It provides maximum gains in efficiency for minimal expenses. It is why AxSTREAM Suite is seriously concerned about preliminary design and design phase at all. Turbo machinery design process in AxSTREAM includes 4 major phases. Design phase. Design phase includes preliminary design and post-design tasks. Main objective of preliminary design is to generate a number of solutions that all suited to design specifications and select the most optimal one. Post-design task deals with single solution chosen by preliminary design. Its task is to adjust the solution to particular design requirements, preserving machine performance. Validation phase is powered with Mealine Streamline Solver. It is integrated with 2 automated multi-point calculations tools. They are DOE-based study optimization tool AxPlan and chart generator AxMap. Profiling blade design phase provides a number of options for profile building. It is integrated with blade 3D design in a single module. 3D Express analysis phase is a final part of analysis. It provides tools to perform FEM-based structural analysis of blades, and CFD analysis of flow phenomena in blade-to-blade channels. Preliminary design process details. Preliminary design process started with design specifications. They include boundary, that is inlet-outlet conditions, and a small number of parameters that governs design process. Typical design parameters are specific diameter, load and flow coefficients, first blade height or exit flow angle. Design parameters can be specified as a range of values. Boundary conditions and design parameters are the input to the first module of preliminary design, solution generator. Solution generator produced a random sequence of sets of design parameters values within specified ranges. Special random search engine produced so-named SOL sequence, that provide best coverage of multi-dimensional search space. Each generated set of design parameters is checked with inverse solver. Successfully solved variants are stored as a solutions in design space. The solution is presented as a point in multi-dimensional space. Each solution point I includes its design parameters values and a number of integral results for the solution. The number of saved design parameters and results define the number of design space dimensions. Second part of preliminary design is Design Space Explorer. It has 2 functions. First, to filter solution by setting limits for particular resulting data, and second, to present design space as a 3-dimensional cube. Any 3 solution parameters may be selected as cube axles. Such presentation allows to estimate at a glance the correlation between different factors. In some sense it is a dynamic, multi-parametric version of well-known Smith diagram. There is a sample of cube projection of design space from turbine preliminary design case. Here are Smith diagram for particular specification, flow coefficient vs entropic velocity coefficient. Efficiency vs number of stages. Efficiency vs minimal reaction. Efficiency vs maximum Mach number. Efficiency vs tip diameter. An additional feature of Design Space Explorer is an ability to validate selected solution with direct task immediately in design space. This way user can find and choose an optimal solution on this early phase of design process. Preliminary design interface is unified for all types of turbo machines, available in AxSTREAM. Some design parameters may be different, but general structure is common. For each module to be designed, the ranges of design parameters have been defined. The random combination of design parameters values that can be solved are stored in design space. User can see it as a points in 3D space. Most prospective solution can be defined using Design Space Explorer. Design Space Explorer provide means to present design points in different dimensions. Table allows to assign integral parameters to design space axes. This way solution set can be estimated at sign. This projection of design space shows efficiency versus isentropic velocity coefficient and flow coefficient. It is an analog of well-known Smith diagram. There is the chart of efficiency versus number of stages. It is evident that efficiency raised when number of stages been increased. Designer has a choice between efficiency and machine weight length. This space shows the dependence of efficiency versus maximum Mach number. Naturally, higher Mach number solution has lower efficiency. The chart of efficiency versus averaged isentropic velocity coefficient. There is a chart of efficiency versus averaged flow coefficient. The solution selected on preliminary design phase is transferred for post-design processing. It allows to adjust profile parameters in S1, that is blade-to-blade plane, and in S2, meridional plane. AxSTREAM provides an option to align flow path along spline. Post-design is powered with inverse task, which adjust cascade angles to keep specified mass flow rate. The direct solver is a central part of the AxSTREAM suite. It provides the final performance estimation for any machine designed in AxSTREAM. The direct solver is intended to solve the so-named direct task of turbine machinery, which is using known geometry to estimate machine performance. Direct solver includes 3 layers. Kernel layer of the direct solver solves a system of 4 classic equations: energy, continuity, process, and state. Middle tier layer is machine specific. It runs calculations dependent on type of turbo machinery. The outermost layer includes loss and fluid models. These models are not integrated in the solver code, but rather exist as dynamic libraries. Such architecture allows the users to easily add new models or custom make new ones. Due to proprietary effective realization, AxSTREAM Direct Solver is able to find a solution for flow paths with up to 100 components, that is 50 stages, and up to 50 span-wise streamlines. For through-flow solutions, the solver uses streamline curvature method. This is why the direct solver is also often named as streamline solver. AxSTREAM Direct Solver runs in 2 main modes. In mainline mode, using mainline geometry, as input and output data is extrapolated on other span-wise sections. In streamline mode, solver takes into account the span-wise geometry distribution and output data is calculated for each span-wise streamline. AxSTREAM Direct Solver can be used via different interfaces. The main of it is Direct Solver Launcher. Launcher allows to specify main boundary conditions and monitor main integral results power, efficiency, mass flow rate. Charts panes embedded in launcher frame shows the streamwise and span-wise distribution of main parameters. It may be blade and flow angle distribution, velocities, Mach numbers distribution, loss distribution, reaction distribution, and so on. Meridional view window presents different aspects of flow path, streamline shapes, flow leakage diagram, velocity triangles, properties distribution in meridional plane, such as pressure, Mach number, and others properties, calculated in AxSTREAM.